All right, this is part B of this problem. In the first video, we looked at the area of region R, shown in green here. On this video, we're going to be looking at the volume of the solid formed when that region is revolved about the x-axis. Now, first, to visualize this, it's a little tricky. You want to visualize this region being revolved about the x-axis in like a circle here. And it's kind of hard to draw, 3D like this. So I do have a tool available for us to look at. I have a graph on Desmos using their 3D graphing to help show. So thought I had it on that board, but here it is. So you can see the region R right here in gray, outlined in red. And then here's this solid being revolved about that x-axis, that region. If we turn it at an angle here, you can really kind of see it's kind of hollow on the inside there. Really a cone shape on the inside because of the line y equals x. When you revolve it around, it just makes like that cone shape. And then on the back side, it's not perfect with the way it graphs it, but it should be a nice smooth circle into that, paraboloid coming out of there. Anyway, that's what the region looks like. I might make some other videos trying to show a little bit more of that, but this is it for this one. Anyway, to find that volume, again, you really want to focus on that ith subinterval. Just like I was saying on the other video, you want to picture what's happening when you take, it doesn't have to be at 2, it's just kind of anywhere in there. Let me put the ith subinterval here, so some rectangle in here, and picture that rectangle being revolved about the x-axis. And that wasn't a very consistent drawing, but you get the idea. Here's the rectangle down here. And they call this the washer method, what we're going to use, because what I'm drawing here, pretty badly, is a washer, like what would go over a bolt, right? If you have a bolt and then a washer is like the area between two concentric circles, like a little wheel, and it's just got this really small width to it, right, that goes over a bolt between the bolt and like whatever it's kind of threading into. And so what we're going to do to get this solid is we're going to just basically make a bunch of these washers and add them together. The same way that when we want to get the area of a region, we add together a bunch of little rectangles, right, to represent the area of the region. And, we take the limit. What the integral does is it takes the limit as the number of the rectangles approaches infinity, so their width gets really, really small. What we're going to do is the same thing, washer for the solid. So we're going to have a bunch of these washers stacked next to each other, and I'm just making the diagram worse now. But we're going to take a bunch of those washers stacked next to each other, and we're going to make the solid that way. So if you picture that ith subinterval, what you need is the area, the cross-sectional area of one of these washers. Okay, so if you took this washer and pulled it out of the board and laid it flat, it looks like this, then how do you get the area of this region here, with a hole in the middle? That's the question. That's the area we need. And so to get the area between two concentric circles, all we need is the area of the big circle minus the area of the little circle. So if you imagine the big circle has radius, let's say big R, its area is just pi times its radius, big R, squared. And then let's say the little circle, the inside circle, has a radius little r. Its area is pi times little r squared. And so if we subtract those two areas, the area of the big circle minus the area of the little circle, then we get the area in between, right? So this is the cross-sectional area. But what are those radii? What are the big and little radius? Well, in our washer on this diagram, there's the center. Let me just did that very badly. The center of the rotation is right on the x-axis. That's what we're revolving around. And so the big radius is this right here. It's the distance from the x-axis, the center of revolution, the thing we're revolving about. It's from there up to this outer curve, the one that's going to be revolved about it on the outside. And that outer curve is just f. And that distance is just f, right? It's the distance from f to, in this case, 0. Okay, it does get more complicated. We revolve something about something other than an axis, like in part D of this problem. But in this problem, it's just about the x-axis. So that distance is just f of x. That's big R. And then little r is this distance from r is g. Okay, and so this area, that cross-sectional area, I'm going to erase part of my washer here just to make some room. That cross-sectional area is just pi times f of x quantity squared minus pi times g of x squared. Now, one other thing we can do, we can actually factor the pi out. So you can do big R squared minus little r squared. And so we're going to do that too. We're going to say that cross-sectional area is pi times f of x quantity squared minus g of x quantity squared. And that's the area of the washer, okay? That's the thing that we're actually going to integrate. Because when you do the integral, kind of scroll down here a little bit. When you do the integral, you're going to have that dx. And dx, just like on a two-dimensional problem when you're finding the area, just like there, dx is the width of that rectangle, right? And we multiply by the height, the top curve minus the bottom curve. Here, dx is still the width. It's the width of the washer. So what we're doing is we're taking the area of the washer, of the face of the washer, and we're multiplying it by that width, and it gives us the volume of that little washer. And so if we added together all the little washer volumes, that's what the integral does. That integral symbol is a skinny s. It's a sum. It's a summation. If you look at the definition of a definite integral, it's a summation. It's adding together all of those things in there. The heights that we're going to put together, if it was just an area problem, times the width. In this case, what we're going to put in here instead of heights of rectangles is going to be areas of washers, those like the cross-sectional area. And so that's what goes in here, the pi times f of x squared minus g of x squared. We're going to integrate the cross-sectional area. In fact, anytime you find a volume with these kinds of problems, that's what we're trying to do, is integrate the cross-sectional area. That's my catchphrase for this unit. I'll say it a million times when I'm doing these problems in class. Integrate the cross-sectional area. When you're stuck on how to find a volume, think, how do I integrate the cross-sectional area? What's the cross-sectional area of the solid? So in this case, the cross-sectional area is pi times f of x squared minus g of x squared, that quantity. I'm going to factor the pi. It's already factored out. I'm going to factor it out of the entire integral because it's a constant, pi is. So I'm going to put it outside. And then inside here, we're going to have f of x quantity squared minus g of x quantity squared. And when you do these solids of revolution, the radii, they are squared separately like this. It's one radius squared minus the other radius squared. That's important to remember because with some other solids, they'll get combined more. All right, so what are f and g? Well, f was square root of x plus 2, and g was just x. So this volume that we want, that's our main setup, and it is pi. Oh, we need limits of integration. It's still from 0 to 4, right? That's how that region is defined for x values. This is all with respect to x, so that's what we're going to use, 0 and 4, because they are the x values for our region. All right, so that volume is pi times the integral from 0 to 4 of f of x squared. Well, that's square root of x plus 2 quantity squared, and then minus g of x squared. Well, g of x is just x, and then squared, and that whole thing integrated, dx with respect to x. So we're going to go ahead and do it. I'll go through this part a little quicker. Square root of x, that's x to the 1/2. When you square this out, we're going to get the square root of x squared, which is just x, plus 2 times square root of x plus 2 times square root of x. So that's plus 4 times square root of x, which is x to the 1/2, and then plus 4, right, if you square out that binomial. And then we have minus x squared still. So this is all just the integrand, the part that we are integrating, still from 0 to 4 dx. And nothing too special here. We don't have to do anything fancy. We're just going to do the power rule all the way through. So we get 1/2 x squared for the first term. For the second one here, we're going to add 1 to the power, so we get x to the 3/2. But then you multiply by the reciprocal because we divide by the 3/2, so 2/3. 2/3 times 4 is 8/3. Then plus 4x, right? That's the antiderivative there. And then the last one, the x squared, it's going to be minus 1/3 x cubed. That whole thing is being evaluated from 0 to 4. And again, there was a pi outside, so don't forget that. That's still multiplied on everything. And so we just have to evaluate from 0 to 4. So when we plug 4 in, we're going to get 1/2 times 16. That's 8 plus 4 to the 3/2. 4 to the 1/2 is 2. 2 cubed is 8. So we're going to get 64/3. Plus, and then 4 times 4 is 16. And then minus 64/3, right? 4 cubed and then divided by 3. Hey, that's convenient, actually. And then when we plug 0, and I'm going to subtract and plug 0 into everything, always check. It's tempting to just think when you plug 0 in, you're going to get 0. Here we do. But that's not always the case, right? If you have like a constant term, I guess you wouldn't from integrating. But if you have e to the x, if you have cosine of x, sometimes you get things that aren't just 0. So double check, make sure. Okay? And yeah, that's really the hard work's done now. We can just cancel out the 64/3 terms. And 8 plus 16 is 24, so we get 24 pi is the volume of that solid. So that one wasn't too bad. The next one, where we go about the y-axis, is going to be a little tricky because we're going to use the washer method again. And it's not actually the better method for this. There's something called the shell method that's not part of AP calculus. I might make a video on that too, but we're going to do it with the washer method. It's still not too bad.